So my name is Maz, and today I'm going to present new features of DIANA 10.1. 2016 was a great day or year for us because we had two major releases. First one was early 2016 in February, DIANA 10, and now towards the end we have 10.1. Both of them were big steps. The first one, we completely changed the whole platforms, introducing the new integrated environment and GUI. And 10.1 is complying additional features and enhancing the quality and the features and functionalities of DIANA with respect to pre and post and solver. So in this presentation, I will talk about what's new in 10.1. We have done several and lots of developments. You can find them in our release notes from our online manual. But if I want to categorize them, I can categorize them into the preprocessor part, the things and the developments and the enhancement that are affecting the modeling part, meshing part, visualization. The part which are related to the solver and kernel in terms of the solution procedures, in terms of the results processing, and also for the post-processing. We have a major development, and one of the advanced features that we are developing here is based on the report generator that enhance and speed up the whole report generation, timing in your procedure and organization. These are basically short outlines of the new developments, so you can find more, as I mentioned, in the release note, and if you need anything else, you can always communicate with us to provide detailed information for your reference. So let's start from geometry part. We have incorporated different modeling features and also import protocols, such as importing IFC file format, Revit plugin, and also creation of Bezier surface based on the cloud of nodes. So there is additional basically features and functionality that these groups have been added to the DIANA import class, and you can take benefit of them in conjunction with your other modeling features. IFC is quite important, such as Revit, because if you have your model already created in that geometry modeler, you can convert them and bring them in DIANA for detailed analysis. So from this point of view, it's very beneficial. It's optimizing your workflow, such as Bezier surface, because also with Bezier surface you can model your certification and train geometry based on the cloud of nodes. That one also is very important, based on the XYZ coordinates of the cloud of nodes that you can import into DIANA. So let's go through them. The IFC format is basically international foundation classes. That's something that you can generate, export from Revit. And if you have a model, for instance, in Revit or any other modeler that is possible to generate IFC format, you can basically transfer your geometry components or bodies based on the solid, based on the shell or the sheet faces, based on the beam width, their associated cross sections, and the material properties that you are assigning to those geometry components. You can transfer all of them as a complete geometry into DIANA. That means DIANA reads them based on the solid and based on the shell, whatever you define over there. And it also transfers the associated material property, geometries, properties such as cross sections and offset. These type of things can be transferred in DIANA. As an alternative, you can import reduced geometry. If you have a reduced geometry, in that case, the basically solid models in your Revit or in your modeler will be transferred to either, if it is a solid volume, to the shell type. If it is a kind of a solid column or solid beam, they are transferred as a 1D beam elements. But however, still you can transfer the material and cross-section and corresponding, say, boundary setup that you already defined, or loads if you have. All those can be transferred in DIANA. So from the modeling point of view, this is very important in terms of the keeping your model information and transfer them in one go into DIANA rather than redoing everything in the analysis package with respect to the modeling package. However, what you need to know, you need to be careful when you import as a reduced geometry, you're importing based on the neutral axis. So when you import your IFC model, you will be ended up with some sort of offset issues that it requires in DIANA to go through the geometry repair operation. I will talk about that in the next slides, but especially when you are using reduced geometry based on the neutral axis, there might be some sort of offset or gap between your connections, between wall and floors, between beams and columns, and this is only because of the position or transferring the model to neutral axis. So we explained about what are the material things can be defined and transferred, the name of the bodies, the name of the materials, the properties of the geometry, all of them are transferred. So you can either do the thinking process in the geometry when you're modeling your structure, or you can transfer them into DIANA, and in DIANA you can do this modification and correction of the names or assignment and alignment of the material properties. Another powerful and good feature that we developed with our partner, a plugin for Revit structure that can be downloaded from our website. I will share all the links, or you can find it from our website. You can download this plugin. There is a very intuitive process. You need to set up and attach that to your Revit modeler. And when you have your structure, when you have your project, you can use this plugin, then program automatically transfers all the geometry information through the Python script ready to be imported in DIANA. So that way you can basically again transfer your shapes, your material, your geometry, sectional properties into DIANA for modeling and further modeling and analysis. So this is again another powerful tool that speed up your modeling process and links your geometry modeler into analysis program. The next one is a conversion of our cloud of nodes to three-dimensional surface, specifically for the geotechnical, tunneling, mining, basically engineers, all of them who wants to model the real stratification and the terrain geometry of your ground. In that case, you may have some sort of boreholes based on the position of them, based on the cloud of nodes. You can import all those based on the Excel sheet or text file into the DIANA program, and program automatically converts them into three-dimensional surface with a very good precision and interpolation for making this realistic topographic surface for you. So having these surfaces enables you to deal either with extrusion or use them as a reference cutting plane and embed them inside a solid box. Then you have one full soil domain. This could be for oil and gas industry or geotechnical application, and based on these intermediate plane, you can easily define your faults or different stratification that you have in the model. In terms of enhancement of modeling tools, we have different methods. We added different methods for creating a circular sheet as a kind of a face, circular face, or circular line, or simple circle, or archetype that basically it generates these type of geometry for you. So here you can see based on the start and 3 points diameter, there are different methods are available that helps you based on the minimum input that you have to create and generate one of these circular shapes or curves that you want to be incorporated with your geometry. Another powerful modeler that we added, or the feature that we added at the geometry level, is basically based on the sweep. So this sweep, it works based on the reference cross-section with one guide line or a wire or curve, how you want to name it. And you can see program automatically, you can say it's basically perpendicular or it's projected, and program generates a solid body out of your 2D section. So this way you don't need to worry about any slope of your curvature in the bridge or any segments. You only need to define the reference guide curve and the one 2D section, then you end up with the final three-dimensional solid model. If you remember, with respect to IFC, I was telling that if you import your reduced geometries, you may have some sort of a gap because of presence of your neutral axis. So everything is going to be reduced from solid to sheet, and these will be located at the neutral axis. Therefore, there might be some sort of a gap. Imagine this is a wall, this is a roof. There will be some gap because of the position of neutral axis that we have in the model. To this end, we have different basically geometry trim or some sort of repair features and functions that you can use them in conjunction with your model to make sure that your connectivity and connections are complying your continuity in the model. So in this particular case, you can see there is a gap between the wall and floor, so you can easily extend the last part of your floor to the wall. Similarly, if you have some sort of flashover, you can manually select which part is part of the model, which part is not, and that way you can eliminate the parts which are not necessarily part of the modeling process. So this is trim, and also we have a multi-trim option that you can basically, if you import solid and these solids imported based on the reduced geometry, you may end up to some sort of flashover geometry. So you can use this trim sheet mutually, and then you ended up with the very nicely trimmed shell elements or the face elements that helps you to proceed with further modeling and meshing. Additional feature that we have is basically in terms of the ease of recognition. You can assign the color to the geometry and the material, so that way you can easily recognize which material property has been assigned, used, or which part of the geometry is unassigned, left literally unattended. So you can basically identify them and go through the assignment of the property to those segments. At mesh level, we also have enhanced and improved a lot. We added the mesh extrusion feature, which based on our workflow that we have in DIANA 10 or 10 plus, is based on the geometry. So we inherit the concept of extrusion at the geometry level. Imagine here we have one sheet. It's a kind of a 2D plate element. We're going to extrude that. We're going to give some volume. By this extrusion, we kind of introduce the extrusion feature into the geometry. Therefore, by inheriting this feature, when we're going to mesh it, program automatically recognize the solid bodies which are generated based on the extrusion. It assigns the extruded mesh, and the ones that are just a solid block without extrusion, it goes for optimization and automatic measure. So in this particular case, you can see there is extrusion, there is a duplication of one part here, and then we have some sort of fill part. Based on that, you can find complete three-dimensional extruded model. And when we mesh this final model, program already knows all these individual segments are extruded. Therefore, I'm going to use extruded mesh for these geometries. So now you can see very nice final model and the mesh for my extruded geometry. Another thing that you need to consider, again, you can extrude based on from 1D to 2D. So we have one line, we extrude line to sheet, then we do that other way around. So now we have one model here, and last panel, we're gonna extrude it here. But the advantage of this extrusion is you need to only assign a seed to one of the edges, because all the rest, because of the attribute of extrusion, program automatically recognizes all adjacent edges and reads the corresponding seed from one of the predefined. So for instance, here I only assign seed here and here at these two corners of these blue rectangles, or here I only assign here. Likewise, I only assign at the bottom and these two, and here in the middle here. By having seeds only on these small edges, program automatically maps and generates the extruded mesh for my final product. To enhance the topology and quality of the mesh, we have also adaptive element size near the curvature feature. You can activate that when you want to mesh the model, and program automatically increases the density of your elements around the curvature or sharp edges. And this is good if you have some sort of maybe some sort of pins, connections, these type of joints. If you have, then program automatically refines the elements over there. Therefore, if you have any stress localization in those areas, you have very smooth transition of your state variables if you want to consider these type of sharp corners. This adaptive seed also is applicable in the 2D and 3-dimensional shapes. Here, for instance, you can see this 3D topographic surface, and there are some sort of curvatures in the space. And these curvatures in the space, you can see how the density of the elements when it's off and when it is on, how this density of the elements are refining the distribution of the elements near the curvatures. Additional features that we added in 10.1 are more control on the meshing properties. So we have different grading at different levels that can be assigned and allocated to either to the basically face or to the edge, and also to the body. If you assign them along the edge, we have different type of control options. Could be division, could be element size, could be gradings. And if you want to assign them to the face, then you have also a different type of distribution plus smoothness in terms of the transition of the elements from your outside to inside or from inside to outside. So you can use these control bars here in the dialog box, and that way you can define this transition, that if you want inside of your model be more dense like this or more coarse like this one. And here you can see a symmetry grading along my boundary. One more visualization that we made it available is at the mesh level, so you can easily see the element local coordinate axis, and these local coordinate axis can be overwritten, changed, modified. In the property windows, you can change the direction, and then in real time in a working environment and working windows see the updated and modified coordinates of your elements. In terms of elements, we made interactive approach for modeling cooling pipes. So now in 10.1, through the GUI, you can go for heat of hydration analysis from A to Z without any need of Python scripting or a text file modification. Everything is fully embedded and integrated, and in a very intuitive procedure, you can define your Young hardening analysis, including the cooling pipe, to simulate the basically hydration process or the temperature gradient that are developing during the hydration. So in this picture, you can see here our 3 circuits that are available to cool the wall, the corresponding mesh, and also my convecting boundary that are assigned to the solid model. You can easily read the temperature, inlet, outlet of temperature for the cooling pipe, likewise for the concrete, the development of that. So you can see how the concrete here is basically hydrating while the cooling pipe is here. So here the temperature is lower. And this is the process of cooling process through certain days. So the full A to Z of the Young hardening analysis is possible now through the GUI in DIANA 10.1. For those who were dealing with the fluid structure interaction, we also made available to create this fluid structure interface in 10.1. So that way you can easily simulate your reservoir and also corresponding fluid structure interface through the GUI, and you can set up the analysis for any type of fluid structure interaction in DIANA 10.1. From element point of view, we have completed the family of mass elements by introducing more 2 and 3 nodes, 3-dimensional line mass elements. The advantage of these line mass elements are when you model nonlinear time history analysis, you have a project, and instead of modeling the whole weight of, for instance, windows or some parts in the model, you can define these line elements and assign a mass to them associated to the weight of those structures that are eliminating through the modeling part. So they're very useful, and you can take advantage of them for 2D and 3-dimensional models to be used in your nonlinear time history analysis or dynamic analysis in general. Furthermore, for connections, we have defined and extended our basically creation of the connections between 2 parts, 2 bodies. This could be automatic, could be 2 splitted parts, could be connection with interface elements, and could be supported part. And also we have incorporated the tying features that you can use. This tying point to line, point to surface, line to line, surface to surface. And also there will be some extra features that will be available soon based on the open interface. What we have enhanced in the interface element also is based on the projection. So if you have 2 bodies that there is a gap in between, you can use the new feature and generate interface in between the gapped areas. So that's very intuitive and useful when you are modeling, for instance, a beam and floor, and you're dealing with the offset of the neutral axis. So your beam and your floor, they have a gap, and the connection of that can be easily defined based on the new interface modeling feature that we have in DIANA 10.1. Furthermore, for our valued clients all over the world, we have incorporated multilingual user interface. We started with our Japanese users, who were basically one of our valuable clients, and we made the GUI also accessible through their language. And soon we will incorporate other languages such as Korean and Chinese to make sure that different people with different languages feel comfortable with the basically interactive GUI and the setup of the program through DIANA IE. At material level, we have enhanced a lot, but because of shortage of time, I go through some of them, but indeed, if you have any question, I would be more than happy to address them. To highlight them, we have extended and incorporated many things with respect to SEP FEA model code. We have extended our crack bandwidth definition from the regular with the crack projection one. We have implemented and verified our engineering masonry model we are proud of that because of very good agreement that we have with the tests that we have from Italy and Netherlands laboratories. We have incorporated a new material model associated to the concrete structures. For those who are dealing with the dynamic analysis, I'm pleased to tell them that we have PML method available, so you can use and take benefit of that for dissipating the energies and waves that are propagating in your medium. We extended our soil model to capture the hysteresis behavior and also smaller strain. We have developed our interface elements such as with the compression and the shear also capture the hysteresis behavior of the opening closing. We extended our reinforcement, embedded reinforcement material property based on the Japanese model code who are dealing with some sort of a hysteresis material behavior similar to what we already have as Minigoto Pinto, Montinoti, and Dodger Spreto. And also we have done other enhancements in the concrete field, such as extension of the performance for fiber reinforced concrete, either steel or synthetic. Great improvement and enhancement for Mekiava-Fukuhara model with certain verification documents, so I will explain them, and many more. So again, please feel free to visit our website, go to the release notes of DIANA10.1 from our online manual, and over there you can see all these developments based on the background theories. Later this week, I'm gonna share on our website two important verification documents. One is associated to the engineering masonry model, the one that we developed here in DIANA FEA company. And we verified the behavior of that with respect to the lab results that we got from the Italy and Netherlands. Likewise, we have a great set of tests and verification that we have done for the Mekiava-Fukuhara model. This is the hysteretic model for concrete based on the energy dissipation, and you can see the very good performance of the program DIANA with respect to different applications. So if you have not registered to our newsletter, please go to our website, register to our newsletter. We're going to inform you where you can download these documents. They're quite significant, about 100-200 pages with the full coverage, background theories, material reference parameter inputs, and the corresponding tests. So feel free to visit them and download. They're free of charge and take benefit of them in your model. So starting from the development that we had with SEP FEA model code, so what we have done, we have incorporated the safety factor in the model code, and by modification of that, all the Young modulus and corresponding parameters are automatically gets updated. So this is very important for those who are dealing with the ULS. And also we have made the calculation of the parameters apparent. So if you select one type of a concrete or a specific setup of your model, then there was always a question, what are the parameters that program considers? So it's no more black box. You can clearly, it's very transparent. You can clearly see what are the parameters that are assigned and what are the parameters that are considered based on the factor of safety in the analysis. Furthermore, for crack bandwidth, so far we had a regular crack bandwidth which was based on the element area, and it was dependent, or element volume, and it was dependent on basically the dimension of your elements, could be plane stress, plane strain, or volumetric or 3D elements. To make it more effective or optimize the results, we have developed and basically incorporated the work of Hovenje, which is literally working based on the projection length of the crack in the element. Long story short, if you have elements with some aspect ratio, so here you can see the length with respect to depth, if there are some aspect ratio are in your model, then it's always better to activate this new development with the projection length in the analysis, so your results will be more accurate with respect to capturing the energy which is available in the element. Otherwise, if there is no aspect ratio in the element, both type of crack bandwidths are more or less giving the same behavior, either the regular one or Hovenje. So we have spent a good time in investigation, understanding, discussing, and implementing our masonry model. We have developed a new anisotropic continuum model, which is basically based on the total strain with some extension for modeling masonry structures. This model is based on basically anisotropy behavior of your model, your masonry, and it's enabled to capture both compression, shear, and crushing behavior. And you can easily, in case of shell elements, you can capture in-plane and out-of-plane shear failure of your masonry models. What is important here is the position or alignment of the bricks. So in the continuum model, we don't deal with the discrete model. We don't know the arrangement and position of these individual bricks. Therefore, when we mesh it, usually it comes up with the unstructured element. So imagine this black line is one element. What we need to do as important factor is, in terms of the definition of the material parameter, we need to make sure that element local x-axis, this is important, element local x-axis is in line with my bed joint. Bed joints are these long mortars, and element local y-axis is in line with my head joint. So that way I can basically define different characteristics of my masonry structure, go through the modeling process. And what is important here, we have defined a new setup here, linearize my material at failure. And since our implementation is based on the finite element, so our model is continuum, no more discrete. What we can do here, if there is a failure happening in one of these elements, program transfer that behavior to linear, and you can continue doing the analysis, and therefore you can nicely capture the expansion of the failure in your structure without divergence. So when there is a crack in the model is anisotropy, is nonlinear till the failure. When it's failed, you can basically continue the analysis because the failed element is at utmost failure. There is no more resistance, but with the linear elastic properties, and you can continue with the analysis. As an alternative, you can define residual stress. So if I go here, the characteristics that we were talking, either you can deal with the tension behavior or compression behavior or shear behavior. So in the tensile behavior, when you have a kind of a loss of stiffness or strength of your element, here that's the point that the model is transferred to the elastic model. As an alternative, you can define 10 to 20% of your peak and define a constant value That means there is always a little amount of a residual strength in the model, and you can proceed with the rest of the loading and analysis for the full complete failure of your structure. So this is your tensile behavior. This is when you have a compressive behavior. When you're dealing with the compressive behavior, you can specify your unloading, reloading is either linear or nonlinear, or basically plasticity behavior. Between 0 and 1, you can play with it, and here, for instance, we can define something between 0.2, 3, 4 to come with some sort of not very sharp and brittle drop, and not secant unloading. So something in between to capture our loading, unloading behavior of the model. However, in the tension, our unloading and reloading is literally secant. For shear behavior, here you can see tau gamma. We are basically working based on, we are working based on the amount of tension and compression that are like burden from the weight of the other bricks to the lower one. We are working based on that and the cohesion. So if our model is basically sheared, that means our cohesion is lost and become some sort of no more value for the cohesion. And again, when we change the loading and unloading direction, this history of the cohesion is important for us to make sure that the model is already sheared or no. So this is one example. You can see the diagonal failure, and also how in DIANA you can read this nice diagonal failure in the model. If you define some sort of shear modulus and define some sort of settings in the material property, then program gets that anisotropy or diagonal failure of your model as an alternative. If you don't do that, then program failure is based on the orthogonal failure. So here you can see the black and red one in terms of the energy dissipation of the model subjected to the actuators and basically cyclic loads. Another model that we have at the concrete level, as I mentioned, is Kotsovos concrete model that is very useful based on the minimum input, that's a compressive strength, and you can use this in conjunction with basically with the large structures. So like these type of platforms, when the minimum, as a rough number, when the size of elements are 1 meter or plus, you can use this model. It gives you very good prediction of the failure. The implementation is based on the multi-directional crack model. And as input, user only need to define compressive strength. So no more else. And for the results, you can nicely see the failure of the model. This model is basically verified and compared with empirical model. And here you can see the relation of the bulk modulus and shear modulus, how they are varying with respect to failure in the model. So if you want any more information, here you can find part of the thesis, and also you may refer to our analysis manual, and you can find out more about this material model that can be used for large scale of concrete structures. Another landmark development that we offer in 10.1 is PML method, is perfectly matched layer method. This method is intended for absorbing the energies or the waves that are propagating in our medium. So imagine we have machinery operating on the top surface on a solid foundation, and by vibration of this you can see the signal and waves are propagating in the soil. The whole strategy is to reduce the size of the soil and use this specific type of elements, PML layers, And through that, we're going to absorb or dissipate the energy or the waves that are propagating in my soil medium. So this way, in terms of the analysis, we consider the soil model small. We extend that several time of the dimension of the reduced soil in the model. And based on that, we can capture the elastic wave propagation in which are kind of developing in our medium. What is important here is the incorporation of the spatial functions that you can define them in conjunction with PML based on different directions that you have in the model. Imagine if this is your X, your Y, and Z, you need to define a kind of special function, 0, 1, that when there is no functionality of the absorption and when there is a full functionality of absorption towards the boundary. So this is very important. At any direction in plane, you need to define these type of functions, 0, 1, and also for the depth, because here you can see when the wave is dissipating and propagating from the bottom part, it should be absorbed towards boundaries. So therefore, you need to define a separate special function, 0 to 1. From 0 is attaching point, is here literally, and 1 at the bottom, to absorb all this energy towards the bottom of your PML model. So this is the way that PML works, but from your, as a user point of view, you need to know we have developed equivalent acceleration, and through this equivalent acceleration, program calculates the force, and this can be applied to the full of your model, to the whole soil and the superstructure together. So this is something that program automatically considers that and multiplies that with mass matrix. So here you can see the purpose is to reduce the soil domain. The blue one is our PML domain. The advantage is any wave that propagates not necessarily perpendicular to my domain, even it could be with some angle, this reflection can be absorbed and truncated through the analysis and through the boundaries. In terms of the definition, as I mentioned, we need to assign this equivalent acceleration. The excitation signal must be applied to the structure, and for that we develop this equivalent acceleration loading, and you can assign that to the body. So this is very important. This should be assigned to the full model, not only to the corner, edge, or point. Another extension and detailed development that we have is for small strain soil model. This one is in conjunction with the modified Morklom, an extension of that with hardened Revit, and that way you can capture the cyclic behavior of your model, hysteretic behavior, and also we incorporate that with our interface element. As I mentioned, when you have a structure, there is between the foundation and soil, there is kind of a connection, and when the model is subjected to earthquake, this interface, the foundation and the soil, they're going to be kind of ramped, close, open, and there will be going through some permanent deformation. And this way, using our new interface element, also you can capture that behavior in soil structure interaction. From the output point of view, we have a new development for those who are dealing with ultimate limit states to find out what was the last converged behavior before final failure. And also we have the relative displacement output. So the first one is when you have a nonlinear analysis and you have a series of steps in terms of your convergence, at certain point you may not reach to convergence, and that's purely to the nonlinearity of your model or full failure of your structure. It doesn't matter. So because of that, we have developed a setup that if you have, for instance, you have a series of output every 4 steps, so 1, 5, 9, 13. So if you go through these steps and, for instance, step 13 didn't converge, then program automatically keep the results of previous converge steps, and you can visualize what was happening till last moment before failure. So then you can narrow the possibilities of localization or your strategy towards advancing of your analysis. Another output that we have developed is based on which can be also used for calculation of the drifts, and that's the relative displacement of the point with respect to some bases for different type of displacement, velocity and acceleration, and you can specify that in the output blocks and in the analysis setup, and you can see and read the reference deformation, for instance, the top roof with respect to the foundation or top roof with respect to the top of the wall. And this is very nice and important. You can assign of these throughout the multi-floors, and then you can nicely read your drift per floor. The last one and another important feature that we have in the post-processing is our report generation feature. This report generation feature is basically integrated in DIANA, and basically it speeds up your modeling and the report generation automatically. So if you have done any setup of this report generation in your model, in your project, you save it, and then, for instance, in the next run, your client is asking some modification, or you want to do some alternative analysis, some sensitivity analysis, this report automatically updates based on the new runs and new modification that you have encountered in the model. It gives various type of output based on the different setup that we have. Could be Word documents, could be PDF, could be latex, could be HTML, and nicely there are hyperlink categorized section put on the different sections, and you can easily reach them. What you can set up here, you can describe the model with the properties, with the analysis setup. You can define your geometry, your material property table, loads, boundary conditions, graphs, mesh, tables, and many more. All this setup can be selected and assigned in your report, and then you can save it with the specification of your project. And anytime if you change any modification in the model, program automatically updates the report generator based on the new modifications. So once again, I would like to thank you all for your time and attention. This recorded session will be available on our website and also YouTube channel. You can refer to that later if you have any questions. Otherwise, you can drop me an email and I would be more than happy to answer your questions. Thank you and have a good day.